Let us begin our journey with a quiet meditation on the nature of time. In our brief human lives, we often experience time as a river, a rushing, urgent current that carries us relentlessly forward. We speak of time flying, of moments slipping through our fingers. Our perspective is one of haste, of a constant and hurried unfolding. But this is not the time of the universe. For the cosmos, time is not a river. It is a vast, deep, and almost perfectly still ocean. It is an immense and patient medium, a quiet, boundless expanse in which the slowest, most subtle, and most profound of all creative processes can take place. This is the process of chemistry. This journey is not about the grand, violent forces of physics, the collisions of galaxies, or the explosions of stars. It is a quieter story. It is the story of matter itself, of its long, slow, and patient journey from primordial simplicity to breathtaking complexity. It is the story of how a universe born with only the simplest of ingredients learned, over the course of billions of years, to build. It is a story of atoms finding each other in the cold, dark void, of molecules forming and breaking, of simple substances giving way to complex structures, and of inert matter through a series of slow, improbable, and beautiful chemical steps, finally waking up. We will travel back to the very beginning, to a universe filled with nothing but a uniform, featureless cloud of hydrogen, the simplest atom of all. We will watch as the first stars ignite, becoming the great fiery forges where the heavier elements, the essential building blocks of our world, are first created. We will witness the death of these stars, the supernovae that seed the cosmos with the raw materials for future worlds. Our journey will then take us to the cold, dark spaces between the stars, where these new atoms learn to hold hands, forming the first simple molecules. We will watch a new solar system coalesce from this enriched dust, and we will focus our attention on a young, molten Earth, a sterile ball of rock and fire, a blank canvas awaiting the first tentative brushstroke of life. We will contemplate the arrival of water, the universal solvent, the medium in which the great chemical experiment of life can finally begin. We will simmer in the primordial soup, and we will witness the most mysterious and profound event in the history of our planet, the emergence of the first self-replicating molecule, the dawn of information and of life itself. This is the story of the slow chemistry of time. It is a story of patience, of persistence, and of the quiet, creative power that is inherent in the very laws of matter. It is a story that connects the fiery heart of a distant star to the intricate biological machinery of the cells in our own bodies. It is the story of how, over the course of 13.8 billion years, the universe, through a series of slow, patient, and beautiful chemical reactions, finally created a part of itself that could look back and wonder and understand. Let us begin our journey in the quiet aftermath of creation. The fire of the Big Bang has cooled. The initial incandescent and unimaginably dense plasma of quarks, gluons, and other exotic fundamental particles has expanded and thinned, and the universe has undergone its first great phase transition. The protons and the neutrons have frozen out of the primordial energy soup. The universe is now a few minutes old. It is a vast, expanding, and almost perfectly uniform cloud of hot, ionized gas. And it is, for all intents and purposes, a universe made of only two simple ingredients. The overwhelming majority of this primordial gas, about 75% of its mass, is composed of the simplest possible atomic nucleus, a single proton. This is the nucleus of hydrogen. The remaining 25% is composed mostly of the second simplest nucleus, helium, which consists of two protons and two neutrons, forged in the brief, fiery furnace of Big Bang nuclear synthesis. There are also trace, almost insignificant amounts of lithium, and that is all. The rich and complex periodic table of the elements that we know today does not yet exist. There is no carbon, no oxygen, no iron, no silicon. The universe is a place of profound and beautiful simplicity. It is a universe waiting to be built. For the next 380,000 years, this simple, hot universe continues to expand and to cool. It is an opaque, glowing fog. The matter exists as a plasma, a sea of positively charged nuclei and negatively charged electrons, all moving too fast with too much energy to be able to join together. The photons of light, the afterglow of the Big Bang, are trapped in this dense, charged fog, constantly scattering off the free electrons, unable to travel any significant distance. The universe is a luminous but featureless haze, and then, when the universe reaches an age of about 380,000 years, and the temperature has dropped to a cool 3000 Kelvin, another crucial threshold is crossed. The universe undergoes its second great phase transition. The electrons are now moving slowly enough that they can be captured by the waiting atomic nuclei. This is the moment of recombination. The single protons capture a single electron to become the first, stable, neutral atoms of hydrogen. The helium nuclei capture 2 electrons to become neutral atoms of helium. This seemingly simple act of atomic formation has a profound and dramatic consequence for the universe as a whole. With the free electrons now bound up into neutral atoms, the universe, for the first time in its history, becomes transparent. The photons of light, which had been trapped in the plasma fog, are now suddenly and completely liberated. They are free to travel, unimpeded across the cosmos. This is the decoupling of matter and radiation. The light that was released at this moment is the light that we see today, stretched and cooled by 13.8 billion years of cosmic expansion as the cosmic microwave background. It is the first, faint and beautiful photograph of the infant universe. Let us take a moment to contemplate the state of the universe at this point. It is now a vast, dark and transparent place. It is filled, almost exclusively, with a thin, diffuse and chemically inert gas of neutral hydrogen and helium atoms. The great, creative fire of the Big Bang is over. The universe has entered a long, quiet and seemingly uneventful period that cosmologists call the Dark Ages. For hundreds of millions of years, the universe is a place of profound and almost perfect simplicity and silence. There are no stars, no galaxies, no planets, no life. There is only the endless, expanding and almost featureless cloud of hydrogen and helium drifting in the dark. The chemistry of the universe is for now frozen. A neutral hydrogen atom is a stable and rather unreactive thing. It is content. It has its single proton and its single electron. It has no need to interact with its neighbours. The universe is a vast cosmic ocean of unrealised potential, but the universe is not perfectly uniform. The cosmic microwave background shows us that there were tiny, almost infinitesimal, fluctuations in the density of the primordial gas, tiny regions that were just a fraction of a percent denser than their surroundings. And in a universe that is governed by gravity, even the tiniest of density fluctuations is a seed. Gravity is a patient and relentless force. Over the vast, slow timescales of the cosmic dark ages, it begins to work on these tiny initial inhomogeneities. The slightly denser regions begin to exert a slightly stronger gravitational pull on their surroundings. They begin to draw in more and more of the surrounding hydrogen and helium gas. The process is incredibly, unimaginably slow. It is a slow-motion collapse that takes place over hundreds of millions of years. The rich get richer. The slightly denser regions become much denser. As these vast clouds of gas collapse, they begin to fragment into smaller, denser clumps. These are the protogalaxies, the first large-scale structures to form in the universe. And within these protogalaxies, the gas continues to collapse into even smaller and even denser knots. As a knot of gas collapses, the pressure and the temperature at its center begin to rise. The gravitational potential energy of the collapsing cloud is being converted into thermal energy. The center of the knot becomes hotter and hotter and denser and denser. The hydrogen atoms are being squeezed together with an incredible and ever-increasing force. And then, after hundreds of millions of years of this slow, patient, gravitational collapse, another final threshold is crossed. The temperature at the core of the densest knots reaches about 10 million Kelvin. At this incredible temperature, the hydrogen atoms are moving so fast and are being squeezed together so tightly that they can overcome their natural electrical repulsion. The nuclei can get close enough for a new and much more powerful force of nature to take over, the strong nuclear force, and in that moment, the first true chemical reaction of the post-Big Bang universe takes place. It is the most fundamental and the most important reaction in the entire cosmos. 4 separate hydrogen nuclei, protons, are fused together through a series of steps to create a single, new helium nucleus. This is the process of nuclear fusion. This reaction does something remarkable. The mass of the final helium nucleus is slightly less than the combined mass of the 4 initial hydrogen nuclei. A small amount of mass has been lost in the reaction, but it has not been truly lost. It has been converted into a pure, brilliant and prodigious amount of energy, according to Einstein's famous equation, E=mc². This sudden release of energy creates a powerful outward pushing pressure, a radiation pressure that finally, after hundreds of millions of years, is strong enough to counteract the inward pulling crush of gravity. The collapse is halted. The knot of gas achieves a state of stable, hydrostatic equilibrium. It begins to shine. The cosmic dark ages are over. The first star has been born. To contemplate this long, slow journey is to appreciate the profound patience of the universe. It is to see that the first, creative act of the cosmos was not a sudden flash, but a slow, quiet, and relentless gathering. It was the story of gravity, working over immense, unimaginable timescales to shepherd the simplest and most abundant substance in the universe, hydrogen, into the dense, fiery cores where the slow, patient, and beautiful chemistry of the stars could finally begin. The universe had taken its first, simple ingredient, and it had built a fire. And in the heart of that fire, the next chapter in the story of cosmic chemistry, the creation of the elements of life, was about to unfold. The long, quiet darkness of the cosmic dark ages has been broken. The first star has ignited, a brilliant point of light in the vast primordial emptiness. This star, born from the slow, patient collapse of a cloud of pure hydrogen and helium, is a new kind of object in the universe. It is a stable, self-sustaining nuclear furnace. It is the first great chemical factory of the cosmos. For the next few million years of its short and brilliant life, this star, and the millions like it that are now igniting across the infant universe, will perform the second great act of cosmic alchemy. They will take the simple primordial elements forged in the Big Bang, and through the slow, powerful chemistry of their fiery hearts, they will create the elements of our world. Let us journey into the core of one of these first-generation stars. The conditions here are almost beyond our ability to comprehend. The temperature is over 10 million Kelvin. The pressure is immense, hundreds of billions of times the atmospheric pressure on Earth. The matter is a dense, seething plasma of atomic nuclei and free electrons, stripped from their atoms by the incredible heat. In this extreme environment, the star begins its primary and lifelong work, the fusion of hydrogen into helium. This process, known as the proton-proton chain, is the fundamental source of the star's energy. It is a slow and patient reaction. The first step, the fusion of 2 protons to form a deuterium nucleus, a proton and a neutron, is incredibly rare and difficult. A single proton in the core of a star like our Sun will wait, on average, for billions of years before it successfully undergoes this reaction. It is the great bottleneck of stellar fusion. But the core of a star contains such an unimaginably vast number of protons that, despite the rarity of the reaction, it is happening constantly, producing a steady and reliable stream of energy that will power the star for the vast majority of its life. For millions of years, in the case of these first massive stars, or for billions of years, in the case of a smaller star like our Sun, this is the only chemical reaction that matters. The star is a simple hydrogen-burning engine. It is in a state of serene and stable equilibrium, a perfect balance between the inward crush of gravity and the outward pressure of the fusion energy being generated in its core. This long, stable period is known as the main sequence, and it is the quiet adult life of a star. But even this long, stable life must eventually come to an end. In the core of the star, the hydrogen fuel is not infinite. Slowly, patiently, over millions or billions of years, the hydrogen is converted into helium ash. A dense, inert core of helium begins to build up at the center of the star. This helium ash cannot, at this temperature, participate in the fusion reactions. It is dead weight. As the hydrogen fuel in the core is depleted, the fusion reactions begin to slow down. The outward pressure of the radiation begins to decrease, and gravity, the relentless, ever-present force, begins to win. The inert helium core starts to collapse under its own immense weight. This collapse has a dramatic consequence. As the core collapses, its temperature and its pressure increase dramatically. The core becomes much, much hotter than it was during the hydrogen burning phase. This intense heat from the collapsing core ignites the hydrogen in the shell of gas that immediately surrounds the core. A new and much more furious phase of hydrogen fusion begins, not in the core itself but in a shell around it. This shell-burning phase produces a huge amount of energy, far more than the star was producing during its main sequence life. This immense outward blast of energy pushes the outer layers of the star, the vast gaseous envelope, outwards. The star begins to swell, to expand to an enormous size. It becomes a red giant, its surface cools as it expands, giving it a reddish hue, but its total luminosity, the total amount of energy it is emitting, is far greater than before. And now, in the superheated, incredibly dense and collapsing helium core of the red giant, the next great step in cosmic chemistry can finally take place. When the temperature at the center of the core reaches about 100 million Kelvin, a new and powerful fusion reaction ignites. The helium nuclei, which had been the inert ash of the previous reaction, now become the fuel for the next. Through a process known as the triple alpha process, 3 separate helium nuclei, which are also known as alpha particles, are fused together to create a single, new and incredibly important nucleus, a nucleus of carbon-12 with 6 protons and 6 neutrons. This is a moment of profound significance in the chemical history of the universe. Carbon is the backbone of all known life. It is an atom of incredible versatility, capable of forming the long, complex and stable chains and rings that are the essential scaffolding of biological molecules. The creation of the first carbon atom in the heart of a dying red giant star is the moment that the universe first creates the essential, chemical ingredient for life. Once the star has a core of carbon, the process can continue. If the star is massive enough, the carbon core will itself collapse and heat up, until it reaches a temperature where carbon nuclei can be fused together to create even heavier elements. Carbon can fuse with another helium nucleus to create oxygen, an element that is essential for respiration and for the chemistry of water. Oxygen can fuse with helium to create neon. Neon can fuse with helium to create magnesium. In the most massive stars, this process continues, creating a series of nested, fusion-burning shells, like the layers of an onion. The outer shell is still burning hydrogen into helium. The next shell is burning helium into carbon. The next is burning carbon into neon, then oxygen, then silicon. Each stage of fusion requires a higher temperature and a higher pressure, and each stage is shorter and more furious than the last. The hydrogen burning phase lasts for millions of years. The helium burning phase lasts for hundreds of thousands of years. The carbon burning phase lasts for only a few hundred years. The final silicon burning phase, which creates the elements around iron in the periodic table, lasts for only a single day. The star has become a frantic, short-lived and spectacular chemical factory, rapidly forging the elements that will one day make up the rocky planets and the bodies of living creatures. But this process of stellar nucleosynthesis has a fundamental limit. The chain of fusion reactions stops at the element iron. Iron has the most stable and most tightly bound nucleus of all the elements. When you fuse elements that are lighter than iron, the reaction releases energy. But when you try to fuse iron into something heavier, the reaction no longer releases energy, it consumes it. And so, in the final, desperate hours of a massive star's life, an inert core of iron ash begins to build up at its center. This iron core is the ultimate dead end of stellar fusion. It cannot be burned. It cannot produce any more energy. The star has now reached the end of its long creative and chemical life. It has taken the simple, primordial hydrogen of the early universe and has transformed it, through the slow, patient and powerful alchemy of its fiery heart, into the rich and diverse collection of elements that are the building blocks of our world. It has created carbon, oxygen, silicon, and iron. But its final and most generous act of creation is yet to come. The star is now a cosmic time bomb, its inert iron core on the verge of a final catastrophic collapse that will trigger the most violent and most creative explosion in the universe, an explosion that will forge the rest of the elements in the periodic table and will scatter the star's precious chemical legacy across the cosmos. The stellar forge is about to become the supernova's gift. The massive star has reached the end of its life. Its heart is a dead, inert ball of iron, the final, incombustible ash of a long and furious series of nuclear reactions. For millions of years, the star has been held in a delicate and beautiful balance, the outward pressure of its fusion energy perfectly counteracting the inward, relentless crush of its own gravity. But now, the fire has gone out, the pressure has vanished, and gravity, the patient and ultimate victor, is about to claim its prize. The stage is set for the most spectacular and most chemically creative event in the entire universe, the supernova. In the final moments of the star's life, the iron core, which is about the size of the Earth but contains more mass than our Sun, is supported only by a quantum mechanical pressure of its own, tightly packed electrons, a state known as electron degeneracy pressure. But as the dead, silicon-burning shell continues to rain down more and more iron ash onto the core's mass quickly exceeds the critical limit that this quantum pressure can support, the Chandrasekhar limit, and in less than a second, the core undergoes a final, catastrophic, and almost instantaneous collapse. The iron core, 1 million miles in diameter, collapses down to a ball of matter only a few dozen miles across. The speed of this collapse is almost beyond comprehension, reaching up to a quarter of the speed of light. The iron atoms are crushed into a state of density that is almost unimaginable, a density that is greater than that of an atomic nucleus. In this incredible high-pressure environment, a new and dramatic process takes place. The immense pressure forces the electrons to combine with the protons in the iron nuclei in a process of inverse beta decay, creating a sea of pure neutrons. The iron core has been transformed in an instant into a single, gigantic and super-dense atomic nucleus, a neutron star. This newly formed, incredibly dense and incredibly rigid ball of neutrons finally provides a new source of pressure, neutron degeneracy pressure, that is powerful enough to halt the collapse. The collapse is stopped, abruptly and violently. The infalling matter, which had been rushing inwards at a quarter of the speed of light, now slams into this hard, unyielding surface of the neutron star, and it bounces. This bounce creates a powerful and colossal shockwave that begins to travel outwards, back through the star. This shockwave is the trigger for the supernova explosion. But for a long time, the computer simulations of this process had a problem. The shockwave, as it travelled out through the dense, overlying layers of the star, would lose energy and would stall. It was not powerful enough on its own to blow the star apart. There was a missing ingredient. We now believe that the missing ingredient is a vast and powerful blast of neutrinos. In the brief, violent moment of the core's collapse, a huge number of neutrinos are created. These neutrinos are ghostly, almost massless particles that interact very weakly with other matter. The vast majority of them stream out of the core and out of the star, carrying away a huge amount of energy. But a small fraction of them, perhaps only 1%, get absorbed by the material just behind the stalled shockwave. This sudden, massive injection of energy is enough to reinvigorate the shockwave, to give it the power it needs to continue its journey outwards and to tear the star apart. The re-energized shockwave now rips through the outer layers of the star, the nested, onion-like shells of silicon, oxygen, carbon, helium, and hydrogen. As it does so, it heats these layers to incredible temperatures, billions of degrees, and subjects them to immense pressures. This triggers a final, explosive, and runaway burst of nuclear fusion, a process known as explosive nucleosynthesis. In the brief, violent moments of the explosion, the lighter elements are rapidly fused into heavier ones, creating a rich and complex cocktail of new elements. But the supernova has one, final, and even more important chemical gift to give. The process of stellar nucleosynthesis, even in the heart of the most massive stars, stops at iron. To create the elements that are heavier than iron, elements like copper, silver, lead, gold, platinum, and uranium, you need a process that can overcome the energy barrier of iron fusion. You need a process that can add neutrons to the existing nuclei, causing them to become heavier and to transform into new elements. The heart of a supernova explosion is the perfect environment for this process. It is a place that is flooded with an almost unimaginable density of free neutrons. In the brief, chaotic moments of the explosion, the existing iron group nuclei are bombarded with a furious and rapid flux of these neutrons. This is the R process, or the rapid process of neutron capture. The nuclei absorb neutron after neutron, becoming incredibly heavy and unstable before they have a chance to decay. Then, after the explosion, these super heavy, unstable nuclei undergo a series of radioactive decays, transforming into the stable, heavy elements that we know. Every atom of gold in a wedding ring, every atom of silver in a photograph, every atom of uranium in a nuclear reactor was created in the fiery, chaotic, and unimaginably violent heart of a supernova explosion billions of years ago. These precious heavy elements are the rare and beautiful chemical legacy of a star's death. The shockwave, now laden with this rich and diverse bounty of newly forged elements, both light and heavy, finally reaches the surface of the star, and the star explodes. In a single, brilliant and spectacular flash, the star can outshine its entire host galaxy, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. This brilliant light is just the announcement of the supernova's true gift. The real gift is the matter itself. The explosion scatters the outer layers of the star, the newly created elements from carbon to uranium, far out into the interstellar medium. The star is returning its substance to the cosmos, but it is returning it in a profoundly enriched and transformed state. The simple, primordial gas of hydrogen and helium from which the star was born has been cooked, processed, and transmuted into the full and glorious diversity of the periodic table. This expanding, glowing cloud of debris, known as a supernova remnant, will continue to travel through the interstellar medium for thousands of years, mixing with the existing gas and dust, and enriching it with the heavy elements that are the essential, raw materials for the next generation of creation. To contemplate the supernova is to witness the profound and beautiful paradox that lies at the heart of the cosmos, that creation and destruction are two sides of the same coin. It is to see that the death of a star is not an ending, but a new beginning. It is the necessary, violent, and deeply generous act that makes the future possible. The supernova is the ultimate act of cosmic recycling. It is the star's final, magnificent, and chemical gift to the universe, a gift that provides the seeds of new stars, of new planets, and ultimately of life itself. The slow chemistry of time has taken a dramatic and explosive leap forward. The universe is now seeded, and the stage is set for the next, quieter and more intricate chapter in the story of cosmic creation. The supernova's violent creative flash has faded. The expanding remnant of the dead star, a ghostly glowing cloud of newly forged heavy elements, continues its slow, inexorable journey into the vast, dark spaces between the stars. Here, in the interstellar medium, this precious chemical gift will mix with the primordial hydrogen and helium that has populated the cosmos since the beginning. The universe is no longer a simple two-element system. It is now a chemically enriched and far more interesting place. But the atoms are, for the most part, still alone. They are individual, isolated points of matter, drifting in a cold and almost perfect vacuum. The next great step in the slow chemistry of time is for these atoms to find each other, to hold hands, and to form the first stable chemical bonds. The universe must learn to build molecules. The birthplace of the first molecules is a place of deep, cold, and profound darkness. It is a giant molecular cloud. These clouds are the largest, coldest, and densest objects in the entire galaxy. They are vast, sprawling, and filamentary structures, hundreds of light years across, containing hundreds of thousands of times the mass of our Sun. They are the great cosmic nurseries, the places where the next generation of stars and planets will be born. From the outside, a molecular cloud appears as a dark, opaque patch against the bright, starry background of the Milky Way, a hole in the fabric of the heavens. This darkness is the key to its creative chemical potential. The cloud is so dense with gas and dust that it blocks the harsh, ultraviolet radiation from the nearby stars. This creates a shielded, protected environment, a cold and gentle sanctuary where the slow, delicate chemistry of molecule formation can finally take place. The temperature inside a molecular cloud is incredibly cold, only a few tens of degrees above absolute zero. At these frigid temperatures, the atoms are moving very, very slowly. This is crucial. In the hot, energetic environment of the early universe, or even in the diffuse, warmer regions of the interstellar medium, atoms are moving too fast. They might bump into each other, but they would immediately fly apart again, their kinetic energy too great for any stable chemical bond to form. But here, in the deep, cold heart of the molecular cloud, the atoms are slow enough that if they meet, they can stay together. But there is still a problem. Even in the densest parts of a molecular cloud, the gas is still an incredibly thin vacuum by earthly standards. The chances of two individual atoms meeting in the vast emptiness of space are incredibly small. And even if they do meet, they have a problem with the conservation of energy. When two atoms form a chemical bond, they release a small amount of energy, the binding energy. This energy has to go somewhere. If the two atoms are isolated in space, the only place for the energy to go is into the kinetic energy of the newly formed molecule, which will cause it to vibrate so violently that the bond will immediately break apart again. To form a stable molecule, you need a third body, something that can absorb the excess energy of the chemical reaction and radiate it away. And this is where the second crucial ingredient of the molecular cloud comes into play, the dust. Mixed in with the vast clouds of hydrogen and helium gas are tiny, microscopic grains of dust. These dust grains are the solid, refractory remnants of the previous generation of stars. They are tiny, irregular specks of silicate rock and carbonaceous soot, coated with a thin mantle of water ice, frozen carbon monoxide, and other simple frozen molecules. These dust grains are the unsung heroes of interstellar chemistry. They are the catalysts, the meeting places, the third bodies that make the formation of molecules possible. Let us visualize the process. A single, cold, hydrogen atom, drifting through the cloud, collides with the surface of a dust grain. At these frigid temperatures, the atom does not bounce off. It sticks to the icy surface, a process known as adsorption. The dust grain is like a piece of cosmic flypaper. Over time, many different atoms, hydrogen, oxygen, carbon, nitrogen, all from the surrounding gas, will collide with the dust grain and will become stuck to its surface. The surface of the dust grain now becomes a busy chemical meeting place. The atoms are no longer isolated in the vastness of space. They are now neighbours, held in close proximity on a solid surface. They can skate across the icy mantle, and when they encounter another atom, they can react. The dust grain itself, with its vast, complex lattice of atoms, can absorb the excess energy of the chemical reaction, allowing the newly formed bond to be stable. And so, on the surfaces of these billions upon billions of tiny, cosmic dust grains, the slow, patient chemistry of the universe begins in earnest. Two hydrogen atoms meet and form a molecule of molecular hydrogen, H2, the most abundant molecule in the universe. A hydrogen atom meets an oxygen atom, and they form a hydroxyl radical, OH. The hydroxyl radical then meets another hydrogen atom, and they form the single, most important molecule for the future of life, a molecule of water, H2O. A carbon atom meets an oxygen atom, and they form carbon monoxide, CO. A stable and abundant molecule that is one of the primary ways that astronomers can trace the presence of these otherwise invisible molecular clouds. A carbon atom meets four hydrogen atoms, and they form methane, CH4. A nitrogen atom meets three hydrogen atoms, and they form ammonia, NH3. Over millions of years, the icy mantles of the dust grains become coated with a rich and complex layer of these simple, frozen molecules. But the chemistry does not stop there. The faint but persistent ultraviolet light from distant stars and the high-energy cosmic rays that can penetrate even into the dense heart of the cloud can provide the energy to break these simple molecules apart and to trigger new, more complex reactions. This energetic processing of the icy mantles can create a surprisingly rich and complex organic chemistry. The simple molecules can be linked together to form longer chains. Methane can be converted into ethane. The reactions can produce simple alcohols like methanol and ethanol. They can produce aldehydes and ketones. They can even produce the simplest amino acid, glycine, the fundamental building block of proteins. The molecular cloud is a vast, cold, and slow-motion chemical reactor. It is taking the simple atomic legacy of the stars and is weaving it into a rich and complex tapestry of molecular diversity. The universe is no longer just a collection of elements. It is now a collection of ingredients. To contemplate the molecular cloud is to appreciate the quiet, hidden, and essential role of the cold and the dark in the creative process of the cosmos. It is to see that the most important chemistry does not always happen in the fiery hearts of the stars, but also in the deep, frigid silence of the interstellar void. It is to recognize the profound importance of the humble dust grain, the tiny catalytic stage upon which the atoms first learn to hold hands, The universe has taken a crucial and patient step. It has moved from the world of the atom to the world of the molecule. The raw materials for planets and for life are now being assembled. The slow chemistry of time is preparing the recipe for the next great act of cosmic creation. The giant molecular cloud, that vast cold and dark nursery of the stars, is not a static object. It is a dynamic, turbulent and restless place. Within its sprawling filamentary structure, the slow, patient and relentless force of gravity is at work, pulling the densest regions of the cloud into ever tighter knots. We have seen how this process leads to the birth of a new star at the centre of a collapsing core. But the story does not end there. Not all of the material in the collapsing cloud falls directly into the central, protostar. The cloud has a small but significant amount of rotation, a remnant of the turbulent motions of the larger parent cloud. And as the cloud collapses, the law of the conservation of angular momentum dictates that this rotation must speed up, in the same way that an ice skater spins faster when they pull their arms in. This rotation prevents a significant fraction of the infalling gas and dust from falling directly onto the protostar. Instead, this material is forced into a vast, flattened and spinning disk that orbits the young star. This is the protoplanetary disk, or the accretion disk. It is the birthplace of planets. Let us take a moment to contemplate this new and beautiful structure. It is a vast, rotating disk of gas and dust, hundreds of times larger than our own solar system. At its centre is the young, hot and luminous protostar, which is still gathering mass from the inner edge of the disk. The disk itself is a place of incredible physical and chemical diversity. It is a dynamic, evolving and complex environment, a vast, slow-motion chemistry experiment that will, over the course of the next few million years, sort, process, and assemble the raw materials of the molecular cloud into a new and stable planetary system. The most important feature of the accretion disk is its temperature gradient. The inner part of the disk, close to the young hot star, is a place of intense heat. The temperature here can be over 1,000 degrees Kelvin. The outer part of the disk, far from the star's radiation, is a cold and dark place, not much warmer than the parent molecular cloud. This steep temperature gradient acts as a great cosmic chemical refinery. It sorts the different materials in the disk according to their condensation temperature, the temperature at which they can transition from a gas to a solid, liquid or ice. In the hot inner regions of the disk, only the materials with the highest condensation temperatures can exist as solids. These are the refractory materials. They are the metals like iron and nickel, and the silicate minerals, the stuff of which rocks are made. All of the other, more volatile materials like water, ammonia and methane can only exist as a gas in this hot inner region. In the cold outer regions of the disk, beyond a crucial boundary known as the frost line or the snow line, the temperature is low enough for these volatile materials to condense into solid ice particles. The outer disk is a place that is rich not just in rock and metal, but also in vast quantities of frozen water, frozen ammonia, and frozen methane. This chemical sorting, this great cosmic distillation, is the first and most important step in determining the fundamental architecture of the emerging planetary system. It is the reason why our own solar system has small, rocky, and metal-rich planets, Mercury, Venus, Earth, and Mars, in its inner regions, and giant gas-rich and ice-rich planets, Jupiter, Saturn, Uranus, and Neptune, in its outer regions. The recipe for the planets is determined by the local chemical ingredients that are available. Now that the ingredients have been sorted, the slow, patient process of construction can begin. The process starts with the tiny microscopic dust grains that we first encountered in the molecular cloud. In the relatively dense environment of the accretion disk, these dust grains begin to collide with each other. At the low relative velocities of the disk, they do not shatter. They stick together through a combination of electrostatic forces and simple mechanical interlocking. This process is called coagulation. Slowly, patiently, over thousands of years, the dust grains grow into larger and larger aggregates. They grow from microscopic specks to pebble-sized objects. As they grow, their gravitational influence begins to become more important. The larger objects, the planetesimals, which are now a few kilometers in size, begin to gravitationally attract and to sweep up the smaller dust and pebbles in their vicinity. The process begins to accelerate. The rich get richer, and they get richer, faster. This is the process of accretion. the planetesimals collide and emerge, growing into larger and larger protoplanets, objects that are the size of our Moon or of Mars. The inner part of the disk is a violent and chaotic place, a cosmic demolition derby of colliding and merging protoplanets. Over the course of a few million years, this process of accretion will sweep up most of the solid material in the inner disk, forming a small number of large, stable, rocky planets. The story is different in the outer disk, beyond the frost line. Here, there is a much larger amount of solid material available to build with, because in addition to the rock and the metal, there are also the vast quantities of ice. This allows the protoplanets in the outer disk to grow much, much larger and much, much faster. They can quickly grow to a mass of about 10 times the mass of the Earth, and when a protoplanet reaches this critical mass, it undergoes a new and dramatic transformation. Its gravity is now so strong that it can no longer just attract the solid, icy planetesimals. It can now begin to gravitationally capture the vast amounts of hydrogen and helium gas that make up the bulk of the disk. This triggers a period of runaway gas accretion. The protoplanet begins to pull in a huge, thick and massive atmosphere from the surrounding disk, growing, in a relatively short period of time, into a true gas giant, like Jupiter or Saturn. The accretion disk is a place of both construction and of migration. The newly formed planets do not necessarily stay in the orbits in which they were born. They can interact gravitationally with the surrounding gas in the disk, which can cause them to spiral inwards or outwards. This process of planetary migration can dramatically reshuffle the architecture of a planetary system, and it may explain the existence of the hot Jupiters that we have observed around other stars, giant planets that are orbiting incredibly close to their parent stars in places where they could not possibly have formed. After a few million years, the young star at the centre of the disk will enter its T-Tauri phase, a period of intense stellar winds and high-energy radiation. This powerful outward blast of wind and light will sweep away the remaining gas and dust in the disk, bringing the era of planet formation to a close. The chemistry of the disk is now complete, the recipe has been followed, the ingredients have been cooked. What is left is a new, stable and beautiful planetary system. It is a system that has been sculpted by the slow, patient and intricate interplay of gravity, of chemistry and of time. The accretion disk has taken the chemically enriched, but largely unstructured material of the molecular cloud, and it has transformed it into a highly structured and chemically differentiated system of worlds. It has created the rocky planets, the gas giants, and the icy comets and asteroids. It has created a home, and on at least one of these newly formed worlds, a small rocky planet in the habitable zone of a nondescript yellow star, the slow chemistry of time is about to embark on its most ambitious, most mysterious, and most beautiful project of all. The protoplanetary disk has cleared. The young sun has ignited its mature fires, and its fierce stellar wind has swept the solar system clean of the primordial gas and dust from which it was born. What remains is a new and still unsettled family of worlds. Our focus now narrows, leaving the cosmic scale behind, and we journey inward to a single, small, and still glowing ember of a planet. This is the young Earth, in the first, violent chapter of its long life, a period known as the Hadean Aeon, named after the Greek underworld. It is a name that is well deserved. This is not the gentle blue and green world we know. This is a planet of pure, brutal, and inorganic chemistry. It is a world of rock and of fire. Let us try to imagine this primordial Earth, some 4.5 billion years ago. It is a molten or semi-molten ball of rock, its surface a glowing, churning, and hellish ocean of magma. The heat that maintains this molten state comes from three primary sources. The first is the leftover accretional heat from its violent formation, the immense energy of a billion colliding planetesimals converted into thermal energy. The second is the heat from the decay of short-lived radioactive elements that were abundant in the early solar system. And the third is the heat from the great, planetary-scale chemical sorting that is now taking place, the process of differentiation. In this molten, liquid state, the young Earth is not a homogeneous ball of rock. The different elements that make it up are free to move, and they begin to sort themselves according to their density, under the relentless pull of gravity. The heaviest elements, primarily iron and nickel, sink towards the centre of the planet. This slow, planetary-scale migration, releases a huge amount of gravitational potential energy as heat, keeping the planet molten. This iron catastrophe is the process that forms the Earth's dense metallic core. The lighter, silicate minerals, the stuff of rock, float towards the surface, forming a vast, global magma ocean. The Earth is transforming itself from a jumbled collection of accreted rubble into a structured, layered planet with a core, a mantle, and a crust. This is the first great chemical ordering of our world. The surface of this magma ocean is a place of unimaginable violence. There is no solid ground. The crust is a thin, black, and constantly shifting skin of cooling rock, like the skin on a pot of hot pudding. This fragile crust is constantly being torn apart, subducted, and remelted by the churning convective motions of the magma ocean beneath it. The surface is a chaotic landscape of volcanic vents, of fissures spewing molten rock, and of vast glowing lakes of lava. And the sky is no more hospitable. The early atmosphere of the Earth is not the gentle, nitrogen and oxygen-rich air we breathe today. It is a thick, dense, and toxic cocktail of gases that have been outgassed from the molten interior of the planet through its countless volcanoes. It is an atmosphere composed primarily of water vapor, carbon dioxide, nitrogen, and perhaps some hydrogen sulfide and carbon monoxide. There is no free oxygen. It is a crushing, suffocating, and poisonous sky. The atmospheric pressure at the surface is immense, perhaps hundreds of times what it is today, and the greenhouse effect of this thick carbon dioxide-rich atmosphere is extreme, helping to keep the surface of the planet molten. And the violence is not just internal. The young solar system is still a chaotic and dangerous place. It is filled with a swarm of leftover debris from the era of planet formation, a cosmic shooting gallery of asteroids and comets. The Hadean Earth is subjected to a constant and ferocious bombardment from space, a period known as the Late Heavy Bombardment. The surface is relentlessly pummeled by impacts, from the small house-sized objects that create fiery streaks in the sky, to the giant, mountain-sized asteroids that can punch through the fragile crust, creating vast, new oceans of molten rock and vaporizing millions of tons of the planet's surface. The greatest of all these impacts, and the most significant event in the early life of our planet, is the one that created our moon. The leading theory, the giant impact hypothesis, proposes that in the first few 100 million years of the solar system's history, the young Earth collided with another Mars-sized protoplanet, an object that has been given the name Theia. The collision was not a head-on impact, but a glancing blow. The energy of this impact was almost beyond comprehension. It would have completely remelted the Earth, turning it back into a global magma ocean. It would have vaporized a significant portion of both the Earth's mantle and the impacting body, Theia, and it would have thrown a vast cloud of this molten, vaporized rock into orbit around the Earth. Over the course of the next few thousand years, this orbiting ring of debris would have slowly, patiently, coalesced under its own gravity, first into a series of small moonlets, and then, through a series of further collisions, into the single, large, and beautiful moon that we know today. Our moon is a child of this ancient cosmic violence. It is made primarily of the lighter, silicate materials from the mantles of the Earth and Theia, which explains why the moon has such a small iron core. The formation of the moon had a profound and lasting effect on the chemical and physical evolution of our planet. The immense tidal forces of the new and much closer moon would have churned the Earth's magma ocean, helping to drive the process of differentiation. And most importantly, the moon's gravity would have a stabilizing effect on the Earth's rotation. It would act as a great celestial anchor, preventing the Earth's axis of rotation from wobbling chaotically. This axial stability would be crucial, billions of years later, for the development of a stable, long-term climate, a climate that would be conducive to the evolution of complex life. Let us take a final moment to contemplate this Hadean world. It is a planet of pure inorganic chemistry. It is a world of geology, of physics, and of violence. There is no life. There is no biology. The slow chemistry of time has so far only been able to create a sterile, molten, and inhospitable ball of rock. It is a beautiful but terrifying world. It is a world that is waiting for a catalyst. It is a world that is waiting for a medium, a solvent, a substance that can cool its fiery surface and can provide the gentle, aqueous environment where the next, more delicate, and more intricate chapter of chemistry, the chemistry of life, can finally begin. The planet is hot, the sky is full of steam, and the world is waiting for the rain. The Hadean Earth is a world of fire, a molten sphere shrouded in a thick, toxic, and steam-filled atmosphere. It is a planet that is, for now, too hot for the chemistry of life. For the next great step in the slow chemistry of time to take place, the Earth needs to cool down. And it needs a medium, it needs a solvent, a substance that can dissolve and transport other molecules, a substance that can provide a gentle, stable, and protected environment where complex chemical reactions can occur. It needs the single, most important, and most remarkable molecule in the entire universe. It needs water. Where did the Earth's water come from? For a long time, the prevailing theory was that all of the Earth's water was endogenous, meaning it was part of the original material from which the Earth was formed, and it was delivered to the surface from the planet's interior through the process of volcanic outgassing. As we have seen, the early atmosphere was indeed composed largely of water vapour, released from the molten rock of the mantle. This is certainly a large part of the story. But in recent years, another complementary theory has gained prominence. This is the exogenous theory, the idea that a significant portion of the Earth's water was delivered to it from space after the planet had formed. The primary delivery vehicles for this cosmic water were the comets and the asteroids, the leftover icy debris from the formation of the solar system. Let us contemplate a comet. It is a beautiful and ethereal object, a dirty snowball of frozen water, frozen carbon dioxide, frozen ammonia, and dust. These comets are pristine, time capsules from the birth of the solar system, preserved in the deep, cold freeze of the outer solar system, in the Kuiper belt and the Oort cloud. In the chaotic early days of the solar system, the gravitational nudges of the giant planets would have sent a shower of these comets and water-rich asteroids careening into the inner solar system, where many of them would have collided with the young Earth. Each one of these impacts would have delivered a cargo of water to our planet. The evidence for this cosmic delivery comes from the chemical analysis of the water itself. A water molecule, H2O, is made of 2 hydrogen atoms and 1 oxygen atom, but hydrogen has a heavier stable isotope called deuterium, which has a neutron in its nucleus in addition to the proton. The ratio of heavy water, water made with deuterium, to normal water can be measured, and it acts as a kind of chemical fingerprint. The deuterium to hydrogen D/H ratio of the Earth's oceans is a specific known value. When we measure the DH ratio of the water in comets, we find that some of them are a good match for the Earth's oceans, while others are not. The current thinking is that the majority of the Earth's water was likely delivered by a specific class of asteroids, the carbonaceous chondrites from the outer asteroid belt, whose DH ratio is a near-perfect match for our oceans. So, the water of our world is a mixture, a cocktail of primordial, outgassed terrestrial water and of ancient extraterrestrial water delivered by a billion, impacting messengers from the cold, outer reaches of the solar system. But having the water in the atmosphere as steam is not enough. For the chemistry of life to begin, the water needs to be in its liquid form, and for that to happen, the Earth needs to cool down. Over the course of hundreds of millions of years, the initial intense heat of the Earth's formation begins to dissipate. The rate of the violent asteroid bombardment begins to decrease. The planet's surface begins to radiate its heat away into space. Slowly, patiently, the temperature of the surface begins to drop, and then a critical threshold is reached. The surface temperature drops below the boiling point of water at the immense atmospheric pressure of the time, and the rain begins. It is a rain that is almost beyond our ability to imagine. It is not a gentle shower. It is a global, torrential, and relentless downpour that lasts for millions of years. The vast, thick, and steam-filled atmosphere begins to condense and to fall to the surface. It is a deluge of truly biblical proportions, a flood that is happening on a planetary scale. This great primordial rain is the most important, transformative event in the history of our planet's surface. The hot liquid water falls upon the still hot volcanic basaltic crust. It cools the rock. It begins to erode the landscape. It fills the great impact basins and the low-lying plains. Slowly, patiently, over millions of years of this relentless downpour, the first shallow and global ocean is formed. The Earth is no longer a planet of fire. It is now a water world. Let us take a moment to appreciate the profound chemical significance of this transformation. Liquid water is a truly remarkable and in many ways a magical substance. It is the universal solvent. The water molecule is polar, meaning it has a slight positive charge on its hydrogen side and a slight negative charge on its oxygen side. This polarity allows it to dissolve other polar molecules, like salts and minerals, with incredible efficiency. The new global ocean is not an ocean of pure water. It is a rich chemical broth, a soup that is filled with the dissolved minerals that have been leached from the planet's rocky crust. Water also has an incredibly high heat capacity. This means that it can absorb and store a huge amount of thermal energy without its own temperature changing very much. The new global ocean acts as a great planetary thermostat, a thermal buffer that will help to stabilize the planet's climate and to protect it from extreme temperature swings. And the density of water has a strange and crucial anomaly. Most substances become denser as they get colder, but water reaches its maximum density at 4 degrees Celsius. Below this temperature, as it freezes into ice, it becomes less dense. This is why ice floats. This seemingly simple fact has profound consequences for the possibility of life. If ice were denser than water, the oceans would freeze from the bottom up, and in a cold period the entire ocean could become a solid block of ice, extinguishing any life within it. But because ice floats, it forms a protective, insulating layer on the surface of the ocean, allowing the liquid water and any life within it to survive below. The arrival of liquid water has completely and irrevocably transformed the planet. It has cooled the crust, it has stabilized the climate, and it has created a vast protected and chemically rich environment. The Earth is no longer a sterile geological object, it is now a laboratory. The stage is set, the ingredients are dissolved, the medium is in place. The slow chemistry of time, which had been confined to the hearts of stars and the cold, dark clouds of space, has now found a new and far more promising home. It has found a home in the warm, shallow and sunlit waters of the primordial terrestrial ocean. The great chemical experiment of life is about to begin. The great primordial rain has ceased. The young Earth is now a water world, its surface covered by a vast, warm and global ocean. The planet has found its medium, its universal solvent. The stage is now set for the most mysterious, the most profound, and the most significant chapter in the slow chemistry of time. This is the story of abiogenesis, the origin of life from non-life. It is the story of how a simple, inorganic, and sterile world, through a series of slow, patient and contingent chemical steps, gave rise to the first living cells. Our journey now takes us into the heart of this mystery, into the warm, shallow waters of the early Earth, into the chemical crucible that has come to be known as the primordial soup. Let us contemplate this early ocean. It is not the clear, blue, and oxygen-rich ocean we know today. It is a murky, greenish-brown and anoxic broth. It is warm, perhaps even hot, heated from below by the geothermal activity of the thin volcanic crust. It is rich in dissolved minerals, leached from the rocks by the hot acidic water. It contains dissolved gases from the atmosphere, primarily carbon dioxide, nitrogen and methane, and it is a place of immense chemical energy. The energy to drive the first difficult steps of organic chemistry comes from a variety of powerful sources. The young sun, with no protective ozone layer in the atmosphere, bombards the surface of the ocean with intense, high-energy, ultraviolet radiation. The thick, turbulent atmosphere is racked by colossal electrical storms, and a constant, furious barrage of lightning strikes the surface of the water. The ocean floor is a landscape of hydrothermal vents, great volcanic fissures that spew a rich cocktail of superheated, mineral-rich water and reactive chemicals, like hydrogen sulfide, into the ocean. And the constant ongoing bombardment of the Earth by meteorites and comets delivers not only water, but also a significant quantity of preformed organic molecules from space. This warm, chemically rich and energy-filled ocean is the primordial soup. It is a vast planetary-scale laboratory, a chaotic and bubbling cauldron of possibility. And in this cauldron, the slow, patient and largely random process of abiotic synthesis begins. The simple, inorganic molecules that are dissolved in the water itself, the carbon dioxide, the methane, the ammonia, are being torn apart and reassembled by the constant influx of energy. Let us imagine a single lightning strike. Its immense energy can break the strong, stable bonds of the water and nitrogen molecules in the atmosphere, creating highly reactive free radicals. These radicals can then recombine in new and interesting ways, forming simple organic molecules like hydrogen cyanide, HCN, and formaldehyde, CH2O. These molecules then rain down into the ocean, adding to the chemical richness of the soup. Or let us journey down to a hydrothermal vent on the deep ocean floor. Here, in the steep chemical and thermal gradients where the hot, alkaline, vent fluid mixes with the cooler, more acidic ocean water, a powerful and natural form of chemical energy is created. This chemiosmotic energy, a kind of natural geological battery, can drive the reduction of the dissolved carbon dioxide in the water, forcing it to combine with hydrogen to form simple, organic molecules like methane and formate. The hydrothermal vents are like great geological engines, constantly pumping a stream of simple, organic fuel into the primordial ocean. Now, the soup is no longer just a collection of simple inorganic molecules. It is beginning to be seasoned with a variety of simple organic monomers, the basic molecular building blocks of life. Formaldehyde molecules can react with each other, in the presence of a mineral catalyst like clay, to form simple sugars, like ribose, the sugar that forms the backbone of our RNA. Hydrogen cyanide molecules can react with each other to form adenine, one of the 4 crucial letters of the genetic code. In 1952, in a famous and iconic experiment, the chemists Stanley Miller and Harold Urey tried to simulate these conditions in a laboratory. They created a closed system of flasks and tubes, containing water, methane, ammonia, and hydrogen to simulate the early ocean and atmosphere. They heated the water to create water vapor, and they subjected the gases to a continuous electrical spark to simulate lightning. After only a week, they analyzed the water, and they found that it had turned a murky reddish brown. It was filled with a rich and complex mixture of organic molecules, and most remarkably, they found that they had created several different types of amino acids, the fundamental building blocks of proteins. The Miller-Urey experiment was a landmark moment in the science of the origin of life. It showed that the transition from simple, inorganic chemistry to complex, organic chemistry is not a difficult or an improbable step. It is an easy, robust, and almost inevitable consequence of the basic laws of chemistry and physics, given the right initial conditions. The universe, it seems, wants to create the building blocks of life. So, our primordial soup is now filled with a rich and diverse collection of these essential organic monomers, the amino acids, the nucleotides, the building blocks of RNA and DNA, the simple sugars, and the lipids, fatty molecules that will be crucial for forming the first cell membranes. The universe has successfully created the letters of the alphabet of life, but having a collection of letters is not the same as having a book. The next, great and far more difficult step in the slow chemistry of time is to link these simple, monomer building blocks together into long complex chains, or polymers. This is the process of polymerization. Amino acids must be linked together to form proteins. Nucleotides must be linked together to form RNA and DNA. This is a much more challenging chemical problem. The process of forming these bonds, a dehydration reaction, actually releases a molecule of water. In a watery environment like the primordial soup, this kind of reaction is not thermodynamically favorable. The excess of water tends to drive the reaction in the reverse direction, breaking the chains apart rather than forming them. So how did the first polymers form? This is one of the great unsolved puzzles in the origin of life. But there are several compelling hypotheses. One idea is that the process happened on the surfaces of evaporating shoreline pools or lagoons. As the water in a tide pool evaporated in the hot primordial sun, the concentration of the organic monomers would have increased dramatically, and the removal of the water would have favored the dehydration reactions, allowing the monomers to link together into long chains. The daily cycle of the tides, the wetting and the drying of the shoreline, could have provided a powerful natural engine for polymerization. Another leading hypothesis is that the polymerization was catalyzed on the surfaces of hot clay minerals, like montmorillonite. Clay minerals have a unique, layered, crystal structure that can attract and bind the organic monomers from the surrounding water. They can hold the monomers in a fixed, orderly arrangement, which greatly increases the chances of them reacting with each other. The mineral surface itself can act as a catalyst, lowering the energy barrier for the polymerization reaction. The clay is acting as a kind of primordial, inorganic enzyme, a template for the assembly of the first, complex biological polymers. Let us take a final moment to contemplate the state of our primordial soup. It is no longer just a simple solution of monomers. It is now a complex and messy mixture, a world that contains not just the letters, but also the first, short, and randomly generated words and sentences of life. It contains a vast and diverse collection of short proteins and short strands of RNA, each with a random sequence. The vast majority of these random polymers would have been useless. They would have had no function. They would have been quickly broken down and recycled by the surrounding environment. The slow chemistry of time is a process of immense and seemingly wasteful trial and error. It is a process of creating a vast combinatorial library of possibilities. But somewhere, in this vast and chaotic chemical library, a single, special molecule is about to be formed. It will be a molecule that has a new and almost magical property. It will be a molecule that can make copies of itself. The era of random, chaotic chemistry is about to come to an end. The era of information, of heredity, and of life is about to begin. The primordial soup is simmering. It is a rich, complex, and chaotic broth of simple organic monomers and the first, short, and randomly assembled polymers. The slow chemistry of time has so far been a process of random chance, of trial and error, of creating a vast and diverse library of molecular shapes. But the universe is now poised on the brink of its most profound and most mysterious transformation. It is about to make the leap from the world of simple, reactive chemistry to the world of information, of memory, and of heredity. It is about to witness the birth of the first self-replicating molecule. This is the moment that the chemistry of the universe becomes alive. In all of modern, terrestrial life, the storage of genetic information and the catalysis of chemical reactions are two distinct and specialized tasks. The information is stored in the long, stable, and beautiful double helical molecule of DNA. The catalysis, the work of building and maintaining, the cell is performed by the complex folded and three-dimensional shapes of the protein enzymes. And the link between these two worlds, the messenger that carries the information from the DNA to the protein-building machinery, is the molecule of RNA. But in the very beginning, it is highly unlikely that this complex, specialized and interdependent system could have arisen all at once. It is a classic chicken and egg problem. You need DNA to store the information to make the proteins, but you need the proteins to replicate the DNA. So which came first? In the 1980s, a revolutionary discovery provided a beautiful and compelling solution to this paradox. A group of scientists, including Thomas Seck and Sidney Altman, discovered that the RNA molecule is not just a passive genetic messenger, it can also act as an enzyme. They discovered ribozymes, molecules of RNA that can fold up into complex three-dimensional shapes and can catalyze specific chemical reactions, just like a protein enzyme. This discovery was a thunderbolt. It meant that RNA, in principle, could do both jobs. It could store genetic information in the sequence of its nucleotide bases, and it could also act as a catalyst, performing the chemical work of the cell. This led to the formulation of the RNA world hypothesis, which is now our leading theory for the origin of life. The RNA world hypothesis proposes that the first living systems on Earth were not based on the complex DNA-protein machinery of modern cells, but were based entirely on the versatile, multi-talented molecule of RNA. In this early RNA world, RNA was the master molecule. It was the genome, and it was the enzyme. So let us return to our primordial soup, with its vast, random library of short polymer chains. The hypothesis is that, by pure, random chance, a single, short strand of RNA was formed that had a very special and very powerful property. It had the ability to act as a replicase, a ribozyme that could catalyze the creation of copies of itself. Let us try to visualize this momentous event. Imagine a single RNA molecule, perhaps a few dozen nucleotides long, floating in the soup. Its specific sequence of bases causes it to fold up into a unique, three-dimensional shape, and this shape, by a lucky chemical accident, happens to be a perfect catalytic pocket for binding to other, individual RNA nucleotides that are floating in the soup. And not just any nucleotides. The shape of the pocket is such that it can bind to the nucleotides and can use another, nearby RNA strand as a template, linking the new nucleotides together in the correct complementary sequence. This first, self-replicating RNA molecule is the dawn of information. It is the moment that chemistry becomes heredity. Before this moment, the creation of a complex molecule was a matter of pure random chance. But now, for the first time, there is a mechanism for preserving and for propagating a specific molecular pattern. The information contained in the sequence of the replicator can be copied, and it can be passed on. The emergence of this first replicator would have triggered a new and powerful kind of chemical evolution. The replicator would begin to make copies of itself, using the abundant nucleotide monomers in the surrounding soup as its raw material. Its population would begin to grow, exponentially. It would begin to dominate the local chemical environment. But the process of replication would not have been perfect. There would have been errors, mutations. Every now and then a copy would be made that was slightly different from the original. The vast majority of these mutations would have been detrimental. They would have resulted in a new RNA molecule that was less efficient at replicating, or that could not replicate at all. These less efficient replicators would have been quickly outcompeted and would have disappeared. But very, very rarely a random mutation would have occurred that was beneficial. It would have resulted in a new RNA replicus that was slightly faster, or slightly more accurate, or slightly more stable than its parent. This new, improved replicator would then have a competitive advantage. It would be able to make copies of itself more efficiently than its rivals. Its population would grow faster, and it would soon become the dominant replicator in the soup. This is the birth of natural selection, acting not on a complex living organism, but on a simple, replicating molecule. The slow, random chemistry of the primordial soup has now been replaced by the powerful, directed, and creative engine of Darwinian evolution. The process is no longer random. It is a process of gradual, cumulative improvement, a slow, patient climb up the ladder of chemical complexity. Over millions of years, this process of molecular evolution would have explored the vast combinatorial space of possible RNA sequences. New and more complex ribozymes would have evolved. A ribozyme might have evolved that could create the nucleotide building blocks from simpler precursors, making the replicator less dependent on the random supply of the soup. Another ribozyme might have evolved that could create lipids, the fatty molecules that could form a protective boundary layer. The RNA world would have become a complex and interacting molecular ecosystem. It would have been a world of competing and cooperating RNA molecules, a world of molecular predators and molecular parasites. It would have been a world of constant chemical innovation as natural selection discovered new and more efficient ways to survive and to replicate. To contemplate the emergence of the first replicator is to stand at the very threshold of life itself. It is the moment that the universe discovers a new and powerful kind of chemistry, a chemistry that is based not just on energy and on matter, but on information. It is the moment that a pattern, a sequence, a piece of abstract information becomes the central organizing principle of a physical system. The journey from a random soup of chemicals to a self-sustaining evolving system of RNA replicators is still one of the deepest and most profound mysteries in all of science. We may never know the exact historical sequence of events that led to this transition, but the RNA world hypothesis provides us with a beautiful, plausible, and powerful framework for understanding how it might have happened. It shows us how the slow, patient, and seemingly random chemistry of the early Earth could have, through a series of logical and comprehensible steps, given rise to the beautiful, information-rich, and deeply creative chemistry that we now call life. The universe has learned to remember. And in doing so, it has taken its first, irreversible step on the long, slow road to consciousness. The RNA world is now a vibrant and dynamic place. The primordial soup has been transformed from a random collection of chemicals into a self-sustaining, evolving ecosystem of replicating RNA molecules. The powerful engine of natural selection is at work, tirelessly exploring the vast landscape of chemical possibility, discovering new and more efficient ribozymes, and driving the system towards ever greater levels of complexity. But this nascent molecular life is still a fragile and precarious thing. It is a life without boundaries. The precious information-rich RNA molecules and their associated helper molecules are floating freely in the open ocean, completely at the mercy of their environment. They are constantly in danger of being diluted, of drifting away from each other, or of being broken down by the harsh, external world. For life to take the next, crucial step in its evolution, it needs to create a sanctuary. It needs to draw a line between self and other. It needs to create a stable, protected, and private internal environment where the delicate chemistry of replication can be controlled, optimized, and shielded from the chaos of the outside world. Life needs to invent the cell. It needs to build a home. The fundamental building block of this first home is a remarkable and ubiquitous type of molecule, the lipid. A lipid molecule has a strange dual nature. It has a head that is hydrophilic, meaning it is attracted to water, and it has a long tail that is hydrophobic, meaning it is repelled by water. In a watery environment, these two-sided molecules will spontaneously, and almost magically, self-assemble into beautiful and ordered structures. They will arrange themselves into a lipid bilayer, a two-layered sheet where all the hydrophobic tails are tucked away on the inside, shielded from the water, and all the hydrophilic heads are on the outside, happily interacting with the water. And this flat sheet will just as spontaneously curve around and seal itself up into a tiny hollow sphere. This is a vesicle, or a liposome. It is the simple, primordial ancestor of the modern cell membrane. The primordial soup would have been filled with these lipid molecules, created either through abiotic geochemical processes or perhaps by the action of some of the newly evolved ribozymes. And so, the oceans of the RNA world would have been teeming with these tiny, empty and spontaneously forming vesicles. Now, let us imagine the fateful and likely accidental encounter. A small, self-replicating system of RNA molecules, a cooperative community of replicases and other helper ribozymes, happens to become trapped inside one of these lipid vesicles. This single chance event is one of the most important moments in the history of life on Earth. It is the birth of the protocell. This simple act of encapsulation has profound and immediate consequences. The RNA molecules are no longer at the mercy of the open ocean. They are now contained within their own, private chemical universe. They can no longer drift away from each other. The replicus and its template are now held in close proximity, greatly increasing the efficiency of the replication process. The raw materials for replication, the nucleotide monomers, can be concentrated inside the cell, providing a richer and more reliable source of fuel for the replicator. The protocell has created its own personal and enriched primordial soup. This new, bounded existence fundamentally changes the nature of natural selection. Before, selection was acting on individual, naked RNA molecules. The fittest molecule was simply the one that could replicate itself the fastest. But now, for the first time, natural selection can act on a collective. It can act on the entire protocell as a single integrated unit. Let us imagine two different protocells. The first one, by chance, has encapsulated a slightly more efficient RNA replicus. It will be able to replicate its genetic material faster than its neighbour. It will produce more daughter RNA molecules, and its internal chemical environment will become more crowded. This internal crowding will create an osmotic pressure that will cause the vesicle to grow by incorporating more lipids from the surrounding environment into its membrane, and eventually the growing vesicle will become unstable and will split into two smaller daughter vesicles, each one containing a sample of the precious genetic cargo of the parent. This is the first primitive form of cellular reproduction. The second protocell, which contains a less efficient replicator, will grow and divide more slowly. Over time, the first protocell, the one with the more efficient internal machinery, will leave more descendants. Its lineage will come to dominate the population. Natural selection is no longer just optimizing the RNA molecule itself. It is now optimizing the entire cooperative system of the protocell. This new cellular context creates a powerful evolutionary feedback loop. Any random mutation to an RNA molecule that benefits the protocell as a whole will now be selected for. A ribozyme might evolve that can help to synthesize lipids, making the cell's membrane stronger or allowing it to grow faster. This would be a huge advantage, and protocells containing this new ribozyme would quickly outcompete their rivals. Another ribozyme might evolve that can create a simple, protein-like pore in the membrane, allowing the cell to more selectively import the specific nutrients it needs from the outside world, while keeping harmful substances out. This would be another massive competitive advantage. The protocell has become a new unit of selection, a new kind of individual. It is a cooperative, a collective, a tiny molecular society where all the different internal components are working together for the common good of the cell's survival and reproduction. The selfish, competitive world of the naked replicators has given way to the cooperative, integrated world of the first cell. Over millions of years of this cellular, Darwinian evolution, the internal machinery of the protocell would have become more and more complex and more efficient. The RNA world would have reached its zenith. The protocells would have developed sophisticated metabolic pathways, all catalyzed by a diverse and powerful toolkit of ribozymes. They would have learned to harvest energy from their environment, perhaps from the chemical gradients of the hydrothermal vents, or perhaps even from the light of the sun. And at some point during this long and creative period, two further great chemical innovations would have occurred that would pave the way for the transition from the ancient RNA world to the modern DNA protein world that we know today. The first was the invention of proteins. Proteins are far more versatile and far more powerful catalysts than ribozymes. A random RNA-based system likely discovered how to translate the sequence of an RNA message into a sequence of amino acids, creating the first simple proteins. This new technology would have been a huge advantage, and the protein-based enzymes would have quickly taken over most of the catalytic work of the cell. RNA, its catalytic role now largely redundant, would have become specialized as the genetic messenger, the role it still plays today. The second great innovation was the transition from RNA to DNA as the primary genetic storage molecule. DNA is a much more stable molecule than RNA. Its double helical structure makes it more resistant to chemical damage and provides a built-in mechanism for error checking and repair. A cell that learned to store its precious genetic information in the more robust and more reliable format of DNA would have had a huge selective advantage. It would have been able to maintain a larger and more complex genome with greater fidelity. DNA became the secure master blueprint, the archival copy of the genetic information, stored safely in the protected central library of the cell. With these two final innovations, the transition is complete. The RNA world has given way to the DNA protein world. The first true modern cell has been born. It is a prokaryote, a simple, single-celled organism, the ancestor of all modern bacteria and archaea. It is the last universal common ancestor, or LUCA. To contemplate the birth of the first cell is to witness the profound, creative power of encapsulation. It is to see that the creation of a simple, physical boundary, a membrane, can fundamentally change the rules of the evolutionary game. It creates a new kind of individual, a new level of cooperation, and a new platform for the evolution of complexity. The slow chemistry of time has built itself a home, and from within the protected sanctuary of this first simple cell, it is now about to unleash a new and powerful chemical force that will transform the entire planet. For perhaps 1 billion years after the origin of life, the world belongs to the prokaryotes. The oceans of the Archean eon are teeming with a vast and diverse population of these simple, single-celled organisms. They are all anaerobes, meaning they live and thrive in an environment that is devoid of free oxygen. The Earth's atmosphere is still a thick anoxic cocktail of carbon dioxide, nitrogen, and methane. The chemistry of life is a quiet, local, and largely invisible affair, confined to the murky primordial oceans. But a new and revolutionary metabolic innovation is about to emerge, an invention that will harness the most abundant and most powerful energy source on the planet, the light of the sun. This is the invention of photosynthesis, and it will trigger a slow, dramatic, and planet-wide chemical reaction that will poison the world, drive the first, great, mass extinction, and ultimately pave the way for the evolution of our own, complex oxygen-breathing life. The first and simplest forms of photosynthesis were likely anoxygenic, meaning they did not produce oxygen. These early photosynthetic bacteria would have used the energy of sunlight to strip electrons from easily accessible electron donor molecules like hydrogen sulfide, H2S, which was abundant in the volcanic early oceans. They would use the energy of these electrons to convert carbon dioxide into the organic molecules they needed to grow. This was a powerful and successful strategy, but it had a fundamental limitation. It was dependent on the local and finite supply of electron donor molecules, like hydrogen sulfide. But then, a new and much more powerful form of photosynthesis evolved in a group of bacteria that we now call the cyanobacteria. These remarkable chemical engineers discovered how to use the energy of sunlight to perform a much more difficult and much more energy-intensive chemical trick. They learned how to split the most abundant and most stable molecule in the entire ocean, the water molecule, H2O. The splitting of water is a difficult chemical feat. The bond that holds the hydrogen and the oxygen atoms together is incredibly strong. But the cyanobacteria evolved a complex molecular machine, a protein and pigment complex called photosystem II, that could use the energy of II, captured photons of light to break this bond, to strip the electrons from the water molecule. This gave them an almost infinite and universally available source of electrons. It was a metabolic innovation that would allow them to colonize almost every sunlit corner of the planet. But this new and incredibly successful metabolic process had a byproduct, and that byproduct was a highly reactive, and for the anaerobic life of the time, a highly toxic waste gas, free oxygen, O2. For hundreds of millions of years, the cyanobacteria flourished in the sunlit surface waters of the ocean, pumping out vast and ever-increasing quantities of this toxic oxygen gas. But for a long time, this oxygen did not build up in the atmosphere. It was immediately consumed by two great planetary-scale chemical sinks. The first sink was the dissolved iron in the oceans. The early oceans were rich in soluble ferrous iron, iron 2+. Oxygen reacts very readily with this dissolved iron, causing it to precipitate out of the water as insoluble ferric iron oxide, Fe3+, which we know as rust. For hundreds of millions of years, as the cyanobacteria produced oxygen, the oceans of the world literally rusted. The iron oxide would precipitate out of the water and would settle to the ocean floor, forming thick, sedimentary layers. These layers, when we see them today in the geological record, are known as the banded iron formations. They are vast, beautiful, and globally distributed rock formations with alternating red and black layers that are a silent geological testament to this ancient, planetary-scale chemical reaction. They are the gravestones of the world's first great pollution event. The second great sink was the rock on the land. As the continents began to form and to rise above the oceans, the oxygen in the atmosphere would have reacted with the minerals on the exposed terrestrial surface, causing the rocks themselves to rust and to weather. For perhaps 500 million years, these two great geological sinks were able to absorb all of the oxygen that the cyanobacteria were producing. The level of oxygen in the atmosphere remained vanishingly low. But these sinks were not infinite. Eventually, the dissolved iron in the oceans was all used up. The rate of geological weathering slowed down, and at some point, around 2.4 billion years ago, the sinks became saturated. The production of oxygen by the cyanobacteria finally overwhelmed the planet's ability to absorb it. And for the first time in the Earth's history, free oxygen began to build up, rapidly and dramatically in the atmosphere. This event is known as the Great Oxidation Event, or, more dramatically, as the oxygen catastrophe, and a catastrophe it truly was for the incumbent anaerobic life that had dominated the planet for over 1 billion years. Oxygen is a powerful and aggressive chemical agent. It is a potent oxidizer, meaning it is very good at stealing electrons from other molecules. For the anaerobic organisms, which had evolved in a world without oxygen, it was a deadly poison. The oxygen would have attacked and destroyed their delicate cellular machinery. It would have broken down their enzymes and their membranes. The rise of oxygen in the atmosphere triggered the first, and perhaps the greatest, mass extinction event in the history of life on Earth. The vast majority of the anaerobic life on the planet was wiped out. The world was poisoned by the waste product of its own, most successful inhabitants. The survivors were forced to retreat into the dark anoxic refuges of the world, the deep oceans, the hydrothermal vents, and the muddy sediments, where they live on, even to this day. The surface of the world, the sunlit aerobic environment, was now the exclusive domain of the organisms that could tolerate, and could eventually learn to use, this dangerous new gas. The rise of oxygen also had a profound effect on the planet's climate. Methane is a powerful greenhouse gas. In the anoxic early atmosphere, the methane levels were likely very high, helping to keep the planet warm, even though the young sun was significantly fainter than it is today. But oxygen reacts with methane, converting it into the much weaker greenhouse gases, carbon dioxide and water. As the oxygen levels in the atmosphere rose, the methane levels plummeted. The planet's greenhouse blanket was suddenly and dramatically thinned, and the Earth, in response, plunged into its first, and perhaps its longest and most severe ice age, a series of global glaciations known as the Huronian glaciation. The planet may have frozen over, almost completely becoming a snowball Earth. To contemplate the Great Oxidation event is to be humbled by the power of life to fundamentally re-engineer an entire planet. It is a story of unintended consequences, of a revolutionary new technology that had a devastating and world-changing impact on its environment. It is a story of pollution, of climate change, and of mass extinction, all happening on a planetary scale 2.5 billion years ago. But it is also a story of profound creative potential. This new oxygen-rich atmosphere, as toxic and as catastrophic as it was for the old anaerobic world, created a new and far more powerful energetic landscape for the future of life. The chemical process of aerobic respiration, the process of burning organic molecules with oxygen, releases almost 20 times more energy than the anaerobic metabolic pathways. This vast, new energetic surplus would be the fuel that would power the next, great, evolutionary leap, the emergence of the large, complex and energy-hungry eukaryotic cell, the ancestor of all plants, all fungi and all animals, including ourselves. The slow chemistry of time had poisoned the world, but in doing so it had also inadvertently created the conditions for a new, more complex and more powerful kind of life to emerge. The catastrophe was also a catalyst. The Great Oxidation event was a biological revolution with profound geological consequences. The slow, patient and persistent work of the cyanobacteria, pumping their toxic oxygen waste into the oceans and the atmosphere, had triggered a planetary-scale chemical transformation. We have seen how this event poisoned the world's oceans, precipitating out the dissolved iron to form the great, banded iron formations. But the chemical reach of this new, oxygen-rich atmosphere was not confined to the seas. It extended to the continents, to the bare, rocky surfaces of the primordial land masses. The arrival of free oxygen in the atmosphere initiated a new and incredibly slow kind of chemistry, a chemistry that would, over the course of the next 2 billion years, fundamentally change the colour, the composition, and the very shape of the terrestrial world. This is the story of the slow rusting of the Earth, the patient geological chemistry that created the landscape we know today. Let us travel back in time to the world before the Great Oxidation event. The continents have begun to form, great, high-standing cratons of ancient granitic rock. But the landscape is a strange and alien one. The colour palette of this world is one of blacks, of greys, and of dull olive greens. The rocks are the colour of the raw, unweathered minerals from which they are made, the dark basalts, the grey granites, the green serpentinites. The rivers that run off these continents would carry sediments of these same drab colours. And the sand on the beaches of the primordial oceans would have been a dark greyish-black, made of grains of pyrite, or fool's gold, and uraninite, minerals that are only stable in an oxygen-free environment. It is a stark, reducing, and almost monochromatic world. Now, let us introduce free oxygen into this environment. Oxygen is a powerful and relentless oxidizing agent. It is hungry for electrons, and it will readily steal them from any susceptible atom it encounters. And the rocks of the Earth's crust are filled with such atoms, particularly with iron. Almost all of the common rock-forming silicate minerals contain a significant amount of iron in its reduced ferrous Fe2+ state. When a molecule of oxygen in the atmosphere, dissolved in a droplet of rain, encounters a crystal of one of these iron-bearing minerals on the surface of a rock, a slow but inexorable chemical reaction begins. The oxygen oxidizes the iron, stealing an electron from it and converting it from its ferrous Fe2+ state to its ferric Fe3+ state. This newly formed ferric ion is not soluble in water. It immediately combines with oxygen to form a new and very stable mineral, hematite iron 2 oxygen 3, or with water to form other iron oxides and hydroxides like goethite. We know these minerals by a more common name, rust. This process is called chemical weathering, and over the vast geological timescales that followed the Great Oxidation event, this slow, patient and relentless process of chemical weathering began to change the face of the entire planet. The surface of the Earth began, quite literally, to rust. The process is almost unimaginably slow. It is a chemistry that operates not on the timescale of the laboratory, but on the timescale of the eon. A single hard crystal of granite might sit on the surface of a continent for millions of years, as the slow, patient work of the oxygen and the water gradually breaks down its constituent minerals. The feldspars and the micas are slowly converted into soft clay minerals, and the iron-bearing minerals like biotite and pyroxene are slowly oxidized, staining the emerging soil with the deep, rich, and beautiful reddish-brown hues of rust. The evidence for this great planetary rusting is written, quite literally, in stone. When we look at the geological record, we can see a dramatic and global change in the nature of terrestrial sedimentary rocks starting around 2.4 billion years ago. Before this time, we find the ancient grey and black sands containing the unoxidized minerals like pyrite and uraninite. After this time, these minerals disappear from the sedimentary record, and we begin to see the emergence of the first red beds. These are vast, thick layers of sandstone and shale that are stained a deep brick red colour by the presence of fine-grained hematite cement. They are the fossilized remnants of the first great rusty deserts and river deltas of the newly oxidized Earth. They are a clear and unambiguous signal that the chemistry of the planet's surface had been fundamentally and irrevocably changed. This slow rusting of the continents had another profound and life-altering consequence. It changed the availability of the essential, trace metals that life depends on. In the older Noxic Ocean, iron was abundant and soluble, while other metals like copper and molybdenum were scarce. The early anaerobic life had evolved a biochemistry that was rich in iron-sulfur proteins. But in the new, oxygen-rich world, the opposite was true. The iron was now precipitating out of the oceans, becoming a scarce and limiting nutrient, and the newly oxidized, terrestrial rocks were now releasing a flood of other, previously unavailable trace metals into the rivers and the oceans. Life had to adapt to this new chemical reality. It had to evolve new, biochemical machinery that was less dependent on iron and that could make use of the newly abundant metals like copper. The evolution of the complex eukaryotic cell and the evolution of our own human biochemistry is a direct consequence of this slow, geological change in the planet's trace metal budget. Our own copper-based respiratory proteins are a distant chemical echo of the slow, patient rusting of the Earth's continents 2 billion years ago. Let us take a moment to contemplate the quiet and often overlooked beauty of this process. We tend to think of rust as a symbol of decay, of neglect, and of destruction. But in the story of our planet, rust is a symbol of a profound and creative transformation. It is the chemical signature of the arrival of oxygen, the gas that would make our own lives possible. It is the process that created the rich, red soils of the world, the soils that would one day support the great terrestrial forests and grasslands. It is the process that painted our planet with the warm and beautiful colours of the desert, the canyon, and the autumn landscape. To look at a red rock is to look at a piece of ancient chemical history. It is to see the ghost of the Great Oxidation event. It is to connect the microscopic metabolic work of a tiny cyanobacterium billions of years ago with the vast geological and landscape sculpting forces that have shaped the world we see today. The slow chemistry of time is not just a story of the oceans or of the atmosphere. It is a story that is written in the very substance of the land itself, a story told in the patient, beautiful, and planetary scale process of the slow rusting of the world. Our journey has revealed a planet that is in a constant state of slow chemical transformation. We have seen the oceans rust, and we have seen the continents change colour. But beneath these visible changes, there is a deeper, more fundamental, and more dynamic chemical cycle at work. This is the great planetary scale engine that regulates the Earth's climate over geological timescales, a slow and majestic process that shuttles the most important, life-giving element, carbon, between the atmosphere, the oceans, the rocks, and the biosphere. This is the story of the carbon cycle, the slow, patient and rhythmic breath of our living planet. Let us begin with the carbon in the atmosphere. In the modern Earth, carbon exists in the atmosphere primarily as carbon dioxide CO2, a trace gas that plays a disproportionately large role in regulating the planet's temperature through the greenhouse effect. The amount of carbon dioxide in the atmosphere is not static. It is the result of a dynamic and delicate balance between the processes that add carbon to the atmosphere and the processes that remove it. The primary, long-term source of atmospheric carbon is the Earth's own geological interior. The carbon is stored in the vast reservoir of the Earth's mantle, and it is slowly but constantly released to the surface through volcanic activity. Every time a volcano erupts, it spews a plume of gases into the atmosphere, and a significant component of that gas is carbon dioxide. This volcanic outgassing is the slow, steady and geological exhalation of the planet. If this were the only process at work, the carbon dioxide in the atmosphere would build up relentlessly, leading to a runaway greenhouse effect that would boil the oceans and turn the Earth into a sterile hothouse, like Venus. But fortunately, there is a countervailing process, a process that removes carbon dioxide from the atmosphere and locks it away in the solid Earth. This is the great geological inhalation of the planet, and it is a process that is intimately tied to the slow, chemical weathering of the rocks that we explored in our last chapter. The process begins with a simple chemical reaction. When carbon dioxide from the atmosphere dissolves in a droplet of rainwater, it forms a weak acid, carbonic acid, H2CO3. This is the same process that gives carbonated beverages their slight tangy fizz. This weak carbonic acid is the primary agent of the chemical weathering of the silicate rocks that make up the bulk of the Earth's continents. When this acidic rainwater falls on an exposed silicate rock, like a granite or a basalt, it slowly, patiently and relentlessly dissolves the rock. The carbonic acid reacts with the silicate minerals, breaking them down and releasing their constituent ions, such as calcium, magnesium and sodium, into the water. In this reaction, the carbon from the atmospheric carbon dioxide is converted into a dissolved bicarbonate ion HCO3- in the water. This process is incredibly slow. It can take thousands of years for a single hard rock to be weathered away, but on a global scale and over geological timescales, it is a powerful and effective mechanism for drawing down atmospheric carbon dioxide. The story does not end there. The dissolved ions, including the bicarbonate, are then carried by the rivers and the streams to the ocean, and in the ocean, a new and biologically mediated chemical process takes place. Marine organisms such as corals, shellfish, and most importantly, tiny microscopic plankton, like the coccolithophores, have evolved the remarkable ability to take the dissolved calcium ions and the dissolved bicarbonate ions from the seawater and to combine them to build their shells and their skeletons. They are performing a precipitation reaction, creating solid calcium carbonate, CaCO3, the mineral that we know as calcite or aragonite. This is a profound and beautiful act of biological engineering. These tiny organisms are taking the carbon that was once a greenhouse gas in the atmosphere, and they are locking it away into a stable, solid, and crystalline form. They are building, quite literally, with the breath of the planet. When these marine organisms die, their tiny calcium carbonate shells rain down in a slow, constant, and gentle marine snow onto the ocean floor. Over millions of years, these shells accumulate in thick sedimentary layers. As these layers are buried deeper and deeper, the pressure and the heat compact and cement them into a new kind of rock, limestone. Limestone is the great geological reservoir of the Earth's carbon. The vast limestone formations of the world, the white cliffs of Dover, the limestone caves of Kentucky, the great fossil reefs of the Dolomites, are all the fossilized remains of countless, microscopic, marine organisms that have, over the course of hundreds of millions of years, patiently and quietly removed the carbon from the Earth's atmosphere and have buried it in the planet's crust. This completes the first great loop of the carbon cycle. Carbon is released from the mantle by volcanoes, it is drawn down from the atmosphere by the weathering of silicate rocks, and it is buried on the ocean floor as limestone. But for the cycle to be a true, sustainable cycle, there must be a way to return this buried limestone carbon back to the mantle. And this is where the slow, majestic and powerful process of plate tectonics comes into play. The ocean floor is not a static place. It is a great geological conveyor belt. New oceanic crust is constantly being created at the mid-ocean ridges, and old oceanic crust is constantly being destroyed at the subduction zones, where one tectonic plate is forced to slide beneath another. When a piece of oceanic crust that is covered with a thick layer of limestone sediment is carried into a subduction zone, it is dragged down deep into the hot, high-pressure environment of the Earth's mantle. Here, the heat and the pressure cook the limestone, driving off the carbon dioxide in a process called metamorphism. This liberated carbon dioxide is then incorporated back into the mantle, where it can eventually be released again through a volcano millions of years in the future. This complete geological carbon cycle, from the volcano to the rock to the ocean to the limestone and back to the volcano, is the Earth's fundamental long-term thermostat. It is a beautiful, self-regulating negative feedback loop. Let us see how it works. Imagine that the Earth gets too warm. The warmer temperatures will lead to more evaporation and more rainfall, which will increase the rate of silicate weathering. The increased weathering will draw down more carbon dioxide from the atmosphere, which will reduce the greenhouse effect and will cause the planet to cool down again. Now, imagine that the Earth gets too cold, perhaps entering an ice age. The vast continental ice sheets will cover up the rocks, and the colder temperatures will slow down the rate of chemical reactions. The rate of silicate weathering will decrease, but the volcanoes will keep on erupting, steadily pumping carbon dioxide into the atmosphere. With the removal process slowed down, the carbon dioxide will begin to build up in the atmosphere. This will increase the greenhouse effect and will cause the planet to warm up again, eventually melting the ice sheets and bringing the planet out of the ice age. This slow, patient and geological dance between the volcanoes and the weathering rocks has been the primary force that has maintained the Earth's climate in a relatively stable, habitable range for billions of years. It is the reason why the Earth has never succumbed to the runaway greenhouse of Venus or the deep freeze of Mars. It is the planet's own innate and chemical wisdom. To contemplate the carbon cycle is to see the Earth not as a static geological object, but as a single, dynamic, and interconnected system. It is to see that the chemistry of the rocks, the physics of the climate, and the biology of the oceans are all intimately and inextricably linked. It is to appreciate the profound and beautiful way in which the planet breathes, a slow, deep, and rhythmic breath that has a timescale of millions of years, a breath that has sustained the conditions for life on our world for almost as long as life has existed. Our journey into the slow chemistry of time has revealed a planet that is constantly breathing, its climate regulated by the vast geological dance of the carbon cycle. We have seen the continents rust and the oceans fill with life, but for the first few billion years of Earth's history, the land itself remained a largely barren and desolate place. It was a world of bare rock, of gravel, and of sterile mineral dust. The continents were vast, empty deserts scoured by wind and rain, but devoid of the rich, complex and living matrix that we know as soil. The next great chapter in the slow chemistry of time is the story of how life conquered the land, and in doing so transformed the very ground beneath its feet. It is the story of the invention of soil, a patient, collaborative, and chemical masterpiece, orchestrated by the first, humble, terrestrial pioneers. Let us travel back to the world of about 1 billion years ago. The oceans are teeming with microbial life, and the first complex eukaryotic cells have evolved. But the land is a sterile and hostile environment. The primary challenge for any organism attempting to colonize the land is the profound lack of water and nutrients. A bare rock surface is a dry and nutrient-poor desert. The essential elements that life needs, like phosphorus and potassium, are present, but they are locked away, in an inaccessible, crystalline form, within the mineral structure of the rock itself. The first organisms to make the leap from the sea to the land were likely the same, hardy cyanobacteria that had transformed the atmosphere. They could form dark microbial crusts on the damp surfaces of rocks, but their purchase on the terrestrial world was a tenuous one. The true, revolutionary pioneers of the land were not a single organism, but a partnership. They were a new, symbiotic life form, a beautiful and resilient collaboration between a fungus and an alga, or a cyanobacterium. This is the lichen, A lichen is a remarkable and almost perfect colonizing machine. The fungal partner, the mycobiont, provides the physical structure. Its tough, thread-like hyphae can anchor the lichen to the bare rock, and they can absorb and hold on to the scarce water from the rain and the dew. The algal partner, the photobiont, is the engine. It is a photosynthetic organism that can use the energy of sunlight to create the organic sugars that feed both itself and its fungal host. It is a self-contained terrestrial life support system, but the true, world-changing genius of the lichen lies in its chemical abilities. The fungal partner is a master of chemical warfare. It secretes a powerful and complex cocktail of organic acids such as oxalic acid. These acids are incredibly effective at attacking and breaking down the crystalline structure of the rock itself. The lichen is, quite literally, dissolving its own rocky home. This process, known as bio-weathering, is a far more rapid and more aggressive form of weathering than the simple, carbonic acid weathering we have seen before. As the lichen dissolves the rock, it liberates the essential mineral nutrients that are locked within it. The phosphorus, the potassium, the magnesium, all of the trace elements that the algal partner needs to thrive are now made available. The lichen is not just living on the rock, it is actively mining it. It is a tiny, slow-motion and self-sufficient geological engineer. When the lichen dies, its small but significant contribution of organic matter, the decaying remnants of its own body, is mixed with the tiny weathered rock particles that it has created. This mixture, this thin, dusty and nutrient-enriched layer, is the first embryonic form of soil. It is a process that is almost unimaginably slow. It can take 1,000 years for a patch of lichens to create a single centimetre-thick layer of this primitive soil. But over millions of years, the patient, relentless, and chemical work of the lichens began to create a thin but life-sustaining mantle of soil on the barren continents of the world. This first, thin soil created the opportunity for the next wave of terrestrial colonists, the first, simple, non-vascular plants, the ancestors of the modern mosses and liverworts. These plants could now gain a foothold in the soil that the lichens had prepared, and they in turn would accelerate the process of soil formation. Their root-like rhizoids would further anchor the soil, preventing it from being washed away by the rain, and they would contribute a much larger amount of organic matter to the soil when they died. But the true, great, soil-building revolution came with the evolution of the first, vascular plants, the first true trees, in the Devonian period, around 400 million years ago. The evolution of the root was a profound geological innovation. The roots of these first trees were powerful, physical and chemical agents. They could physically pry apart the cracks in the bedrock, breaking the rock down into smaller pieces, and they would actively secrete their own organic acids and enzymes, dramatically accelerating the chemical weathering of the rock and the release of its mineral nutrients. The evolution of the forest was the moment that the process of soil formation went into overdrive. The vast interconnected network of roots created a deep, stable, and three-dimensional architecture for the soil. The constant shedding of leaves, branches, and eventually the entire tree created a massive and continuous influx of organic matter. This leaf litter would accumulate on the forest floor, forming a new and vital component of the soil, the humus. Humus is the dark, rich, and spongy material that is formed from the slow, partial decay of organic matter by a vast and complex community of soil organisms, the bacteria, the fungi, the earthworms, and the insects. Humus is the very heart of a healthy soil. It is a chemical marvel. It can hold vast quantities of water, acting as a natural sponge that regulates the moisture of the forest. It is rich in the essential nutrients that the plants need, and it releases them slowly over time as it continues to decay. And it provides the physical structure, the light, airy and crumbly texture that allows the plant roots to breathe and to grow. The forest is not just growing in the soil, the forest is actively and constantly creating the soil. It is a beautiful, self-sustaining and positive feedback loop. The better the soil, the healthier the forest, and the healthier the forest, the better the soil it creates. To contemplate the chemistry of the forest is to see the soil not as a simple, inert substance, but as a living, breathing, and complex ecosystem. It is a slow, chemical reactor that is constantly cycling nutrients, storing water, and sequestering carbon. It is a world that is built on the patient and often invisible partnerships between the plants, the fungi, and the countless microscopic decomposers that inhabit it. The creation of soil was one of the most important transformative events in the history of our planet. It changed the chemistry of the land, the flow of the rivers, and the composition of the atmosphere. It created the stable, fertile, and life-sustaining foundation that would allow for the evolution of the great terrestrial ecosystems, the grasslands, the jungles, and the forests that we know today. It is a powerful reminder that the world we inhabit is not a static stage upon which life performs. The world itself is a product of the slow, patient, and creative chemistry of life. The ground beneath our feet is not just rock and dust. It is the living, breathing, and beautiful legacy of 1 billion years of patient and collaborative biological work. Our journey has been one of constant chemical transformation, of matter being assembled, disassembled, and reassembled into new and more complex forms. We have seen life emerge, evolve, and engineer the very planet it inhabits. But the slow chemistry of time is not just a story of creation, it is also a story of preservation. It is a story of how the fleeting, ephemeral, and organic structures of life can be transformed through a slow, patient, and geological process into the enduring, inorganic, and beautiful substance of stone. This is the story of the fossil, a story of how a living being can become a part of the Earth's eternal geological memory. Let us begin with a death. An organism, perhaps a trilobite crawling on the floor of an ancient Cambrian sea, or a dinosaur drinking from a Cretaceous river, comes to the end of its life. In the vast majority of cases, this is the end of its physical story. The soft tissues of its body are quickly consumed by scavengers and are broken down by the relentless chemical work of the decomposers, the bacteria and the fungi. The harder parts, the shell, the bones, the teeth, may last a little longer, but they too are eventually ground down by the physical forces of erosion and are dissolved by the chemical action of the water. The organism's constituent atoms are recycled, returned to the great biogeochemical cycles of the Earth. There is no trace left of its individual existence, but very, very rarely, under a specific and fortunate set of circumstances, a different story can unfold. For an organism to have a chance of becoming a fossil, it must first escape this process of immediate and total recycling. The most important requirement is rapid burial. Imagine our trilobite dies, and its hard, chitinous exoskeleton settles to the seafloor. If it is quickly covered by a layer of fine-grained sediment, perhaps from a submarine landslide or the slow, constant rain of mud from a nearby river delta, it is suddenly and effectively removed from the outside world. It is protected from the scavengers. It is sealed away from the oxygen-rich water that would drive its decay. The burial is the first, crucial step. It is the moment that the organism is transferred from the realm of biology to the realm of geology. Now, a new and much slower kind of chemistry begins. The organism is entombed within the sediment, which, over the course of millions of years, is being buried deeper and deeper by the accumulating layers above it. The pressure increases, the temperature rises, and the groundwater, a slow-moving chemical broth that percolates through the tiny pore spaces of the sediment, begins its patient and transformative work. The most common and the most beautiful form of fossilization is a process called permineralization, or petrification. This is not a process of the original material turning into stone. It is a process of replacement, a slow, molecule-by-molecule substitution of the organic for the inorganic. The groundwater is rich in dissolved minerals, the same dissolved minerals that are the product of the chemical weathering of the continents. The most common of these are silica, the mineral that makes up quartz, and calcite, the mineral that makes up limestone. As the groundwater seeps into the buried remains of the organism, it penetrates into the microscopic, porous structures of the bone or the shell. The conditions within these tiny protected spaces are now perfect for the process of mineral precipitation. The dissolved minerals in the groundwater begin to come out of solution, forming tiny microscopic crystals within the pores of the original organic material. The organic material itself is slowly, gradually dissolving away, but as each organic molecule is removed, a mineral molecule takes its place. It is a slow and incredibly faithful chemical substitution. Over millions of years, this process continues until the original organic material has been completely, or almost completely, replaced by a perfect stone replica. The fossil is no longer a bone or a shell. It is now a piece of rock, a piece of quartz, or a piece of calcite, but it is a piece of rock that has preserved, with breathtaking fidelity, the intricate three-dimensional and microscopic structure of the original living organism. We can see the fine cellular structure of a dinosaur's bone, or the delicate growth lines on a trilobite's shell, all perfectly preserved in the hard, enduring medium of stone. There are other, rarer forms of fossilization, other chemical stories that the Earth can tell. Sometimes the original organic material is not replaced, but is simply compressed and altered. In the case of the vast Carboniferous forests, the buried trees were not petrified, but were slowly, chemically transformed by the heat and the pressure into the carbon-rich substance of coal. A piece of coal is a fossil, a chemical ghost of an ancient tree. Sometimes, an organism can leave behind just an impression. A dinosaur walks across a muddy floodplain, and its footprint is quickly buried by a new layer of sediment. The mud hardens into rock, preserving the shape of the footprint as a trace fossil, a fossil not of the organism itself but of its behavior, of its life. And sometimes, in very rare and very special circumstances, even the soft, delicate tissues of an organism can be preserved. An insect can become trapped in the sticky, golden resin of a tree. The resin then hardens, over millions of years, into the beautiful translucent substance of amber, entombing the insect within it, in a state of almost perfect three-dimensional preservation. A woolly mammoth can fall into a crevasse in the Siberian permafrost and can be flash-frozen, its skin, its hair, and even its last meal preserved for tens of thousands of years. To contemplate a fossil is to hold a piece of deep time in your hand. It is to connect, in a direct and tangible way, with a world that is millions, or even hundreds of millions of years old. A fossil is a story, a message from the deep past, written in the slow, patient and beautiful language of chemical transformation. It is a testament to the remarkable ability of the Earth to preserve the memory of its own biological history. The fossil record is a vast but profoundly incomplete library. The chances of any single organism becoming a fossil are infinitesimally small. The story that the fossils tell is a story with many missing pages and many missing chapters, but it is the only story we have. And it is a story that has been written for us by the slow, patient, and remarkable chemistry of stone. It is the story of how the fleeting and the fragile can be made eternal, of how life can be remembered, and of how a simple, dead creature can be transformed into a beautiful and enduring messenger from another world.